Hi, this video is going to cover the electrolysis of molten ionic compounds, and also if you're doing higher tier we're going to have a quick look at ion-electron half equations. So what exactly is electrolysis then? Well, one useful definition for electrolysis is that it is the splitting up or the breaking up of ionic compounds into the elements that make them up using electricity. Now, ionic compounds as shown in the model have a giant ionic lattice structure which is composed of positive metal ions and negative non-metal ions. You might actually recognise the structure which is shown. It's the structure of the sodium chloride lattice, which is composed of positive sodium ions and negative chloride ions. This lattice is held together by strong ionic bonds, and all ionic compounds are solids at room temperature, and unfortunately for us they are all electrical insulators, which means no electrolysis for solid ionic compounds. The reason that electrolysis doesn't work for solid ionic compounds is that they don't conduct electricity because the metal and non-metal ions cannot move freely since they're trapped inside a giant ionic lattice. However, if we heat a solid ionic compound above its melting point, it will form a molten liquid, or as it's often called, a melt. And in this melt, the ions are free to move, and the molten ionic compound will conduct electricity. Similarly, if we dissolve an ionic compound in water, the giant ionic lattice structure is broken down and the ions are free to move in this solution. This means that solutions of ionic compounds will also conduct electricity. We call these melts and solutions which contain free-moving ions electrolytes. A definition for electrolysis that was mentioned earlier was the splitting up of ionic compounds, that is, compounds which contain metal ions and non-metal ions, into the elements that make them up, using electricity on an electrical current. Another way of looking at it is electrolysis simply turns ions back into atoms. A typical cell for an electrolysis experiment of a molten ionic compound is shown. The cell contains a battery or a cell, two electrodes, one called the anode and one called the cathodes. These electrodes can be made of metal, but are more often than not simply made of graphite because it is inexpensive and a good conductor of electricity. The cathode is connected to the negative terminal of the cell and therefore has a negative charge, while the anode is connected to the positive terminal of the cell and has a positive charge. A bulb or an ammeter can also be placed in the cell to show that an electrical current is flowing. The electrolyte in the cell shown is molten sodium chloride, which contains positively charged sodium ions and negatively charged chloride ions. Once the electrolysis process starts, electrons will leave the cell and travel down the wire towards the cathode, giving it a negative charge. The positively charged sodium ions in the molten electrolyte will then be attracted to this negatively charged cathode. Ions which head towards the cathode are often called cations. Now at the cathode, the sodium ions pick up an electron and are reduced to form sodium metal. An equation to show this reaction is shown. Now the sodium metal melts just below 98 degrees Celsius, and since the electrolysis cell is operating around 800 degrees Celsius, the sodium metal formed will collect as a liquid on the top of the molten sodium chloride. The reduction of the sodium ions to sodium atoms at the cathode is only one half of the reactions taking place in the electrolysis of molten sodium chloride. The other half reaction takes place at the anode. Here, the chloride ions are oxidized to form chlorine atoms. That is, the chloride ions lose an electron, which is transferred onto the anode and returns back to the cell to complete the circuit. Chlorine gas, which is a diatomic gas, is released at the anode. Here, two chlorine atoms simply join together to form a molecule of Cl2 gas. A half equation for the oxidation reaction of the chloride ions to chlorine atoms is shown. Now the chlorine gas which is released at the anode is a diatomic gas. This simply means it is a small molecule made up of two chlorine atoms. It is formed when two chlorine atoms at the anode simply join together to form this new chlorine molecule. This means that the overall half equation for the oxidation reaction at the anode needs to be multiplied by 2. As a quick summary so far, we can say that the cathode is a negatively charged electrode in an electrolytic cell, and as such the positively charged metal ions will be attracted to this negatively charged electrode and will be reduced here. That is, the metal ions pick up electrons from the cathode to form metal atoms. Now, metals from group 1 of the periodic table, such as lithium, sodium and potassium, will have a +1 charge and will gain 1 electron, while group 2 metals, such as magnesium and calcium, will have a 2+ charge, and these metal ions will pick up 2 electrons from the cathode, while a group 3 metal, such as aluminium, will have a 3+ charge and it will gain 3 electrons at the cathode. Right, now the positively charged anode will attract the negatively charged non-metal ions, or anions as they are often called. Most of the anions that you are likely to meet will be the halide ions, that is chloride ions, bromide ions and iodide ions, and you could also meet the oxide ion O2-. These anions or non-metal ions will all lose electrons when they reach the anode and will be oxidized to form non-metal atoms. The half equations shown illustrate these oxidation reactions which take place at the anode. However, a complication is that most of these gases produced at the anode are diatomic, and so each of the half equations will need to be multiplied by 2.